R square value, where is it? Okay, 0.95. 95% of the variability in the estimated volume can be explained because of the girth square. So see what quickly, if you want to analyze and conclude, what you can see is if this value here is lesser than your chosen significance level, that means keep it. If it is more, we can ignore it. It will not add much difference to your analysis. Visualizing this model, okay, which plot volume of trees versus the girth linear regression model. Multiple linear regression is same what we discussed in the, I think the example also which has been taken here is same. So we just see, yeah, the same scatter plot on delivery data set. I hope you remember this n prod distance delivery time. So that same example for multiple linear regression has been used here. Same projectile to show you that now this time you will not have, I think one small topic is left and we'll do that and then maybe we'll end this. Because this you have already done, I'll not do it again. Adjusted R squared also we have already talked about what is adjusted R square. Yeah, this one. Generalized linear model. Now, generalized linear model talks about what we have studied in logistic regression. See the same example coming up again. Based on age and weight, you want to predict whether the person will have a coronary heart disease or not. So it will be either 1 or 0. Now, in order to use linear regression model, there were some assumptions that my y values or the errors which will come when I start predicting. Let's say I have used a linear regression model here to do this modeling, and then I have started predicting what if the age is 99 and weight is 40. Let's say it has given heart disease, yes, and so on. Okay, now you start making comparisons, find the errors. Your error will be uh, if your y is 1, y hat is 0, or it is 0 and it is 1. So this will be static. Only two values will come. Either the error will be 1 or the error will be 0, isn't it? There are only two possible values. But the assumptions of your linear regression says that your errors should be uniformly distributed, normally distributed, which is not the case in this. This calls for a binomial distribution. This is not normal distribution. This speaks binomial distribution. Either two values. Bi means two, either 0 or 1 in the error component. So for this, it is not a good idea to go for direct linear regression algorithms. Maybe we can use enhancement of it. A generalized model of the linear regression we'll use. And that model, what we have discovered was logistic regression, isn't it? So here this is talking about logistic regression model only. We can generalize the linear regression model to fit it to such kind of situations. An example for the generalized linear regression is our logistic regression, which we have already studied. Now what happens here? What if instead of getting y, instead of predicting 1 0 1 or 0, if I predict probabilities, that probabilities will lie in a certain range 0 to 1. So maybe somewhere it will be predicted probability 0.36, somewhere it will be predicted probability 0.98. So a continuous distribution, a continuous normal distribution between of data between 0 to 1 I'll get. Then I can use regression algorithms for it. Okay, so these generalized models will have three components. One is they are internally based on regression techniques. So this standard equation the systematic standard equation which we have seen for linearity will be there. Y is equal to m1 x1 plus m2 x2 plus so on. Now you have some random component also. Random component, like there was e earlier. You have seen in exponential regression there was e raised to the power x which we transformed by taking log. So there is some random component and there is some systematic component. So there has to be something which can connect these two, the systematic and random component. That function is called as a link function. Link function. So if you remember, in logistic regression, we have used a sigmoid function. And what is the equation of sigmoid function? Sigmoid function equation is 1 upon 1 plus e raised to the power minus x. And what was this x? This x, okay, this x is, it can be represented by m0 plus m1 x1. Hardly 5 minutes I'll take, plus m2 x2, not more than that, m2 x2 and so on. A linear equation. This x here can be replaced by a linear equation which is dependent on your predictors. These are your predictors. So what we have done, we have transformed this linear equation and used this link function. This is called link function. We have used sigmoid link function to link my exponential component and my linear equation to establish a connection between that random component exponent and the linear component, which was this. So in all, it becomes a function, and that function we call it as a link function here. So in case of logistic regression, we have used this. Inverse of the logistic function, inverse of this logistic function will be your logit function. So logit function, if you find, it gives you log p upon 1 minus p, which is nothing but this. So what was it doing? See, if you forget about the mathematics, broadly what we were doing, find probabilities, and then the probabilities can be mapped to the 0 and 1. So this function, logit functions, what it does is it maps the probability values from 0, 1 to any range, maybe the probabilities range which you are expecting, maybe minus infinity to infinity, to some real numbers. This logit function does it. The reverse of it is this function, the logistic regression, the logistic function, which is this. This is link function, or you call it logistic function. So this logistic function will do what? It will do the reverse. It will take some random numbers and give you a probability 0 or 1. So exploiting the linear equation to find the categorical attributes is what we were doing in logistic regression. Here we have that same defaulter data set where we want to predict whether the person is a defaulter or not. So we have at balance, we have income, we have student, yes or no. So these are categorical attributes, and defaulter is also a categorical attribute which we want to predict. So we'll be using logistic regression to do this. Scatter plot, if you do, it gives you constant values because the final predictions are not uniformly distributed. They are only two values. Binomial, this shows you binomial distribution of Y values. Train, test, split your data, take 75, 25 rows here. Now build logistic regression and get the values of logistic regression is internally regression. So it also gives you intercept and coefficient, which is coming to be these values. Now put these values in this equation, the sigmoid function, link function here, and this gives you the probability. Checking the accuracy of on the training data, testing data, 97%. This model is accurate. You can create confusion matrix also, and this confusion matrix, I think we have discussed already how confusion matrix is read. This means 2415 rows were there where people were defaulter and it was predicted as defaulter. 7%, 7 were non-defaulter were predicted as defaulters. 54 defaulters were predicted as non-defaulters. Like this you can read, and you can go for accuracy of this as well. So the accurately predicted instances were on the diagonals, this and this. Take a sum of this and divide it by all, you get the accuracy. Accuracy from confusion matrix, which is again coming to be 97.56. Earlier, how we have checked this using score, that is also coming to be nearly this. Different ways of finding the accuracy of the model, of validating the model. I think we are done, and I know people are waiting for they want to go for lunch, so I'll not waste much of your time. But see, we are done for this session, guys. Go through this, and after this, we are left with one more topic, which is time series analysis. Maybe
Yes. We'll have this session on the 13th, which is Tuesday. Thank you, Sonam.
Thank you, Prithvi. Thank you, everyone.
Yeah, I have already posted the link for the regression